My name is Tahi, and I'll be presenting our work Beyond Being Real, a sensory motor control perspective on interactions in virtual reality. Virtual reality as a medium has been receiving a lot of attention recently, with metaverse promising a new way in which we'll interact with digital content. But when we take a closer look at some applications, for the most part, they're just replicating the real world. There's often this fixation on realism and the illusion that what you're experiencing in VR is real, that you're really there. The seminal paper, Beyond Being There, challenged this notion in the early 90s. Holland and Stornetta argued that when we imitate a medium, by definition the imitation will never be as good as the real thing. They encouraged us to instead think about the strengths of computationally mediated communication and collaboration, and presented a framework around needs, media, and mechanisms. Inspired by this work, we present Beyond Being Real, focusing on VR interaction design, more specifically interactions that require movement, such as locomotion, selection, and manipulation, and we present a framework through the lens of sensory motor control for describing interactions that go beyond what's possible in the real world. There are a lot of examples of beyond real interactions in the literature. For example, while walking in the real world is pretty slow, in VR we can overcome this limitation by amplifying every step that we take. So by remapping our movements in space, we can travel much faster when walking in VR. When we reach out to touch an object, there's no reason that we'd have to be limited by the physical constraints of our body. By remapping a body representation, our virtual arm could extend much farther. We can even make it easier to catch or hit a fast-moving object by remapping time. So by not limiting ourselves to replicating the movements in the real world, we can gain lots of benefits and can make interactions more efficient, ergonomic, and accessible. But to effectively tap into the power of these beyond real interactions and to understand the challenges around designing them, we need to consider how we receive sensory information and perceive the world, and how in turn we act and move in the world. In our paper, we first situate VR interactions within the context of what we know about sensory motor control. We then present a framework through this lens to help us better describe beyond real interactions. We conduct a survey which highlights that as a community we've been thinking about these beyond real interactions for a long time. However, we are missing a roadmap for how to move forward. So we discuss the open challenges and argue that the sensory motor perspective can point us towards predictive models and more systematic investigations for beyond real interactions. We'll start by looking at how the human brain plans and controls movement. Imagine you want to reach out and touch an object. In the brain, your intent is converted into motor command signals. This is sent to your body, which results in your arm moving forward. But this movement is subject to noise, changes in the environment, and other unpredictable factors. So the brain needs to evaluate the current state. And it does this using the sensory inputs that it receives. You see your arm moving in space, and you also feel the forces in your arm. This sensory feedback then allows the brain to estimate the current location of your arm and to compare it to where it expected your arm to be. And based on the error, it can correct the control signal. We can think of VR as a subsystem that intercepts these sensory signals. When you move your real arm, this movement is tracked in the VR system and mapped to the virtual renderings. So while you sense the forces in your real arm, you see your avatar's arm moving in VR. So one way we can describe beyond real interactions is that they apply a transformation that is not a one-to-one mapping. And the movements in the renderings don't mirror what is sensed and tracked from the real world. This creates a discrepancy in the sensory feedback. The forces in your arm give you information about where your real arm is, but where you see your virtual arm gives you contradictory information. This model is important for studying beyond real interactions because it captures the sensory conflict that results from the applied transformations, which ultimately influences users' actions. We further simplify this model to create the building blocks for our framework. We use internal model to describe parts of the brain that handle learning new policies and adapting to new dynamics. And the remaining components are the real world, the VR system, and the beyond real transformations. In our framework, we focus on what is being captured from the real world, what aspects of the environment and the user's physical and cognitive state What is the transformation that is being applied to the real-world movements? How are we remapping space, body representation, or time? And what is rendered in VR? Is the remapping invisible until after users move in space? Or are there egocentric or exocentric signifiers that help the internal model have appropriate expectations and predictions in advance? This framework will provide us with a unified way of describing beyond real interactions that captures how movements are transformed and how those transformations are perceived by users. As HCI practitioners, we need to be able to evaluate usable designs from a large design space of possible transformations. And to do so, we need to fill in some gaps in our understanding. We need to study how multisensory processing and integration is done across different sensory systems and how that influences and is influenced by the internal model. We believe our framework will be useful as we move towards better understanding the implications of the sensory conflict that results from beyond real transformations. We conducted a literature survey across relevant HCI conferences, categorizing VR interactions as reality-based, illusory, which create minimal sensory conflict that is unnoticeable by users, and beyond real. Our key finding was that while over the years many new beyond real VR interaction designs have been presented, only less than a quarter of these papers at all mention the human sensory system, and the majority of those are limited to using self-reported measures such as the Simulation Sickness Questionnaire. But it is important for us as a community to consider challenges other than simulation sickness and to perform deeper model-based analyses in addition to the empirical approaches we currently take. In our paper, we highlight some research questions that remain. For example, instead of focusing on physical realism, how can we design interactions that seem plausible to users? And we discuss the importance of causal relationships between the user's actions and the resulting sensory feedback. While initially beyond real interactions are unfamiliar, and the user's internal model can't predict the outcome of their actions, over time there's evidence that users might be able to develop new control policies and learn new remappings. But which design alternatives lead to such motor learning? There also haven't been many longitudinal studies, so we don't know how long it takes for users to learn and adapt, and how might after effects carry over into the real world. We talk about how these are likely task and modality dependent. Finally, VR users have different sensory motor abilities and different physiological and emotional responses to experiences, which all influence motor control. So how can we better capture, model, and adapt to these individual differences? We believe this lens of sensory motor control is key not only for describing beyond real VR interactions, but also as we move towards predictive models that allow us to design and evaluate usable interactions that take advantage of what's possible in VR.